Hey there, let's dive right into this explainer on the crazy, dangerous world of electrical short circuits. When electricity violently jumps off its intended path, the results are, well, explosively dangerous. So what exactly happens under the hood when a steady flow of power suddenly turns totally chaotic? Basically, a short circuit is just a rogue shortcut that forces the electrical potential difference to zero. With absolutely zero resistance to slow things down, this rogue path triggers a massive chaotic energy release. The fallout? It's violent. We're talking extreme heat, melting metal, massive electrical arcs, and seriously deadly fires. Now, engineers categorize these dangerous events into two main groups: symmetrical and unsymmetrical faults. We've got a triple line to ground fault right next to a standard triple line fault. The absolute worst case scenario? A bolted three-phase symmetrical fault. It literally unleashes maximum destructive stress. But unsymmetrical face-to-earth faults are way more common. They actually cause about 90% of all failures. If left unchecked, these massive electrical surges could literally cripple our entire power distribution network. Which brings us to a huge question. How do engineers actually calculate this invisible danger beforehand? They use super rigorous standards like Cellex EN69 to mathematically model those prospective short-circuit currents. The math involves drawing one-line diagrams, mapping out system impedances, and figuring out the equivalent voltage. And you know what? These exact calculations are the secret to correctly sizing our grid's protective equipment. Engineers find the exact symmetrical breaking current to make sure a circuit breaker safely extinguishes the fault. Because if a surge exceeds the breaker's limit, it blows up, potentially causing massive, widespread blackouts. Properly sized breakers act like fast-acting bouncers, safely isolating only the damaged, faulted part of the circuit. Right, so strict safety regulations demand we always prepare for that absolute maximum short-circuit current. But as our power demands totally skyrocket, are we actually doing enough to upgrade our grid's protection?